Alrighty, so sorry about the static a bit earlier. So what this I'm going to talk about here is about how ODE113 kind of works. Same thing goes for ODE45. Just basically how all these numerical integrator solvers things work and how you actually use them, or how you think about them. So when you think about like the situation at hand, it's kind of like throwing and catching a ball. You can imagine a person standing over here, a person standing over there. You're throwing a ball, or in our case, a satellite, over so that it ends up at the position that you want it to. You can imagine starting at an initial position and at an initial velocity. Then what you do is you let the ball fly in the air, just cruise along until it reaches the position that you want it to. If you change the position that you started, but keep the same velocity, you end up with a different curve altogether. That too, if you change your velocity, so into something like this, might go something higher, and it might end up at the same position that you wanted to. What I mean to say is different positions and different velocities will end up at different locations and will end and create different curves. May result in the same location, but like as in may end up with different curves. So what you're trying to do is based off the initial position and the initial velocity, you can map out the entire curve. And that's what ODE solvers basically do, at least for our case for orbital dynamics. So like overall, the system of equations, the system of differential equations that we're dealing with is simply the two-body problem, right? We have r double dot, which is the vector, that's the acceleration, minus mu on r cubed, that's your distance cubed, times the vector r, that's your position, times this business is equal to your acceleration. You know, we already know this part, I think. So you can also split this up into x, y, z coordinates. X double dot, y double dot, z double dot is equal to minus mu on r cubed, x, y, z. Now from here, you can also, so what an ODE solver does is that it kind of like deals with things always in like first derivatives in some sense. What you can think about is, you can think about it as the derivative, so derivative against time of x, y, z is just going to be its velocity. X dot, y dot, z dot. Right? And then you can also think about it that your derivative of your velocity is acceleration. X dot, y dot, z dot is the acceleration. That's x double dot, y double dot, z double dot. Nice. Now, we already defined our acceleration though. We can write it in terms of x, y, and z. So I can write this as minus mu on r cubed, x, y, z. Right? So what I can do though is I can define a state. A state just tells me all key information about a system. In our case, the state here is your position and your velocity. If you change those two, you change the entire system, you change the entire way the thing maps out. And that's all you need to draw out the entire curve. All you need is a velocity and a position. So what I'll do is I'll describe the rate of change of that state of this velocity and position. And I just want to describe how that changes, that's all. Once we know how that changes, we can let the solver figure it out in some sense. So what I can do is I can say that the rate of change, what I'm going to do is I'm just going to like concatenate these, just join these up. X, y, z, x dot, y dot, z dot is equal to, now the rate of change of x has to be x dot. So what you can imagine the code doing is picking this up and then just grabbing it and throwing it over there, because we already defined what these are. We know what y dot is, and we also know what z dot is, because we gave that. Now from here, we can figure out what the acceleration is. That's a minus mu on r cubed, x, and then minus mu on r cubed, y, minus mu on r cubed, z. Right, now because you already gave it what x, y, and z is, then it can actually figure out what each of these accelerations are as well. So now once it figures out what each of these each of these velocities are, and each of these acceleration, it can apply that to a change in x, y, z, x dot, y dot, and z dot. So you can imagine what the code does is that you give it an initial state. You give it like x1, y1, z1, and then x dot 1, y dot 1, z dot 1. You give it an initial state. You tell it, okay, this is what I'm going to start off with. Now from here, it figures out how much does it change. So at the next time stamp, or whatever it decides to do the next time, it figures out what each of these are. Because you defined it, you told it, okay, this is what the acceleration, the velocity is. This is what the acceleration is. And so it simply adds this to what was there before. So, you know, like that, the change in velocity is change in position, sorry, is velocity times time. And then the change in velocity is acceleration times time. So you just get this change, the velocity and acceleration, and then multiply by the amount of time, and then add it to whatever is there. So what the ODE solver does is that it figures this out, and then it just adds it on to whatever's there, and it makes the next term. It makes x2, y2, z2, x dot 2, y dot 2, z dot 2. So it just figures out the next values for it according to the differential equation. And then it just repeats that on and on and on, again and again, until however long you want it to. So what I'll do is I'll apply this to the situation for an orbiting Saturn around the Sun. So you can imagine first what we need to start off with is an initial position and an initial velocity, just like this. If you tell it, okay, this is where I'm starting and this is how fast it's going in this direction, then what it can do is it can plot it, it can pass it along in one point, it can treat it like a straight line, and then it can figure out the velocity and velocity, acceleration, position, and everything from that point. Then it'll figure out, okay, this is the next point, this is the next point, this is the next point, and so on. It follows all the way through. So now from here, let's start off our initial conditions. So now we're trying to model Saturn's orbit around the Sun here. So imagine our Sun, and I need to start off a particular position on of Saturn's orbit. So for my convenience, I'm just going to assume that it's a circular orbit. Clearly, it's not always the case, but the key thing that we're trying to take away is how to model the ODE in orbital dynamics. So imagine Saturn's like directly like down from the Sun. Imagine this is like my little y-axis. This is my x-axis, x, y, and then it has a velocity across this way. So it's perfectly horizontal, and this is perfectly below the Sun, just because it's convenient to me. You can start at any position and any velocity, but it works the same principle. Yeah, so now I can start this with an initial coordinate. The coordinate over here could be given as, now we know the radius of the orbit, which is 715 times 10 to the 6, so that's about like 750 million kilometers. Now the x-coordinate is going to be 0. The y-coordinate is just that, 715 times 10 to the 6. And then my z-coordinate, I'm just going to say that this is perfectly like in plane, so that way we don't have any z-coordinates. You can make these non-zero. These can be whatever values that you want it to be. Just for my convenience, I'm just choosing these. Now, this velocity, I can also define. Now, it goes perfectly horizontal, so that means my velocity is 9.68. Now, the y-coordinate is going to be 0 for the velocity, because it's not going up or down yet. And then the z is going to be also 0, because it's not going up or down, like into or out of the page. So this is your velocity, and this is your your initial velocity and your initial position. Now from here, we can actually just let it code. So you give it the two-body problem, give it these differential equations for it to solve, and it plots each of those positions that you want it to. So that's what we're going to do on MATLAB now. So first you need to tell it how long is it going to simulate. So your t-span, or ts, I'll call it. Now, your starting time is probably 0. Depends on the situation, but generally it's 0. And then how long you want it to simulate. So for me, I'd probably like it to simulate maybe like one period, so 29.4 years. Because I did everything in seconds, so I have to convert into seconds. So that's 29.4, 365 days in a year, 24 hours in a day, and 3,600 seconds in an hour. Nice. So this is the amount of time that I'm simulating, just 0 and then the final time. So however long between those two. Now, you need to tell it your initial state, so your initial position and your initial velocity. So let me start off with my initial velocities, initial position, sorry. I'll call it xi, and that's my initial position. And so what that is going to be the value that I just said above. 0, 715 times 10 to the 6 and 0. 0, 715 times 10 to the 6 and then 0 there. And then we also got our velocity, which is going to be 9.68, sorry, 9.6800. Okay. 9.6800. Nice. Okay, now we have to define the initial state. So that's just combining these two together. So I'll call it XO, or I'll call it PO, because I just call everything in terms of P, so I'll just put it in P as well. It really doesn't matter the name, it's just like, it's just a bit of code here. So here we just put our initial position, xi, and an initial velocity, vi. So that's basically the initial state. So that tells us like all of this. We just defined all of that. Now we need to tell it how should it like, how does each of these change? So this is what this function down over here does. You can practically copy this. This line of code is basically the same for any ODE solver. Now from here to figure out how everything changes. So P over here is your state. So that tells you all six: x coordinate, y coordinate, z coordinate, x velocity, y velocity, z velocity. So let's just like separate that out, just because it looks more convenient that way. So let's say x is equal to p1, the first value of p. Y is equal to the second value of p, and on and on. Just you can skip this part if you feel like it. And then x dot, y dot, and z dot. So p4, y dot is equal to p5, 5, and z dot is equal to p6. You can also change this function so that it depends on mu as well, and then you can define mu outside the function, which is way more convenient. So I can also define what mu is for the sun. Put that up on the top over here. Mu is equal to, what was that? Where'd it go? Give me a minute. I think it was, wait, it was 1.327 times 10 to 11. 1.327 times 10 to the 11. Okay, cool. Now, now it calls in t, p, and mu. Mu is already from before. T and p is what the ODE solver deals with. Okay, so now the function already knows what mu is. So now from here, all I need to tell it is how each of these changes. So first I can say that, yeah, so that means, I'll call this p dot, I'll call it dpdt. Yeah, just change the names over here. Doesn't really change very much. Just make sure that all the names align and match up. All right, so I can say p dot is equal to, actually not p dot, so dpd. Actually, yeah, why not? dp dt is equal to. Now, what's the rate of change of all of these? So, how does x change? It changes by x dot. How does y change? Y changes by y dot. Likewise, z changes by z dot. Okay, now how does x dot, y dot, and z dot change? It changes by mu over r cubed. Now we haven't actually defined what r is though, so we should actually do that over here. So r is equal to, it's just going to be the magnitude of x, y, and z. It's going to be the distance that the planet is away from the sun. So I can just define it as the square root of x squared plus y squared and z squared. I could just do that. Alternatively, you could also just define it as the norm. Norm takes the distance between, yeah, it takes the length of a particular vector. So I could just say x, y, z. Both mean exactly the same thing. Choose whichever you feel like. I'm going to put it as a comment, but it works exactly the same way. And then so what I can do is I can literally type that up now. Mu over r cubed times x. Just put this in brackets so that it's like nice and tiny in some sense. Times x. And then I do the same thing for y and z. Note that this has to be a column vector and not a row vector. A row vector kind of messes up. For some reason, it just doesn't work. A column vector looks nice. and it just works. The other way that you can think about it is just because it's run the simulation all vertically, it just works fine like this. I think it's just in a format that that MATLAB can take easily. Now, okay, so you figured out how this state changes. It tells you how x changes, y changes, z changes, how x dot changes, y dot changes, and z dot changes. These are all the accelerations. These are all your velocities, and tells you how this state changes. And then what it does is that it records each of these states at every time interval. So if you run it now, there's a bit of code that was done a bit wrong. What happened? Oh, call it DPTT. That's right. Okay, just the name of this, it didn't actually match. So I didn't actually know what I was talking about. Okay, now it works fine. Right. Okay, looks cool. Now from here, this is actually like this is the value, all of our states. I just transposed it over here, just because it's easy to read when it's horizontal. Okay, so this is all your x positions over here. These are, every single one of these is your x position. So what it does is that it takes this 9.68, multiplies it by the change in time, and then tells you that's your change in position. And then it figures out the change in velocity, multiplies it by the change in time, tells you this is now your new change in position. And it does that over and over again and again, on and on, for each time it's across. Yeah. Yeah, and then it does that for each of these x, y, and z. Same thing, x, y, and z up here. And then from here we can actually just plot it. So now what you want to do is, generally what you're looking for is plotting the trajectory, how it looks like, the path. So then what I can do is plot 3. Plots 3 coordinates. So now you're looking at your x coordinate, y coordinate, and z coordinate. So that's first, second, and third row. So now you're looking at P, that's the name of the matrix. Now you're looking at the first row, every column, that over there. Now you're looking at the same thing, P, second row, every column. And likewise, you're doing P of the third row, every column. And that's it, you're plotting it. And then you can put title and labels and everything. Oh, wait. Wait. I think the brackets don't match. Oh, no, wait, I did the wrong colon. Whoops. And this is how it looks. There we go. Ta-da! This is our circular little orbit of Saturn around the Sun. The other thing that you should also notice is that if you change the mu value, like if you use the wrong mu values, say for example, if I did 10 to the 20 or something, right? This is actually in meters, but all my other units are in kilometers, so that's why it's not going to match. I'm going to have a bit of an error here. Generally, an error like this, what that means is that your thing kind of just like it kind of fell into the sun. You see your 0, 0, 0, that's your origin here, that's where the sun is. So this is your initial position and velocity and everything, and it launched it, it went, but the thing is it kind of fell into the sun. So whenever you have a simulation error like this, generally it means that it fell into the sun. Not always, but it's generally because of a singularity, which is basically like divide by 0. I can't really work with that. That's why you got to be careful with your units and the way that things are coded in MATLAB. But yeah, that's basically how ODE solvers work. And yeah, I hope it made you guys kind of understand this better. Good luck.